Okay, here we go. It is October 23rd, 2020 at 1:36 p.m. We're in fourth block, room 409 with Principles of Engineering, the second course of Project Lead the Way Engineering program. We are going to try to look at activity 214, which I assigned this week, but did a very poor job of explaining any of it, especially since I'm throwing out most of the instructions as they're given. Obviously, I still want you to do a notebook entry, and I still want you to take a note on every paragraph you see in the introduction and in the resources. The resources themselves, yes, take a note from each slide. However, there's examples that I don't think it's necessary to take notes from the examples, because you're going to be doing the problems actually, when you do the procedure itself. Oh, by the way, close your laptops, please, and look at my big screen. Nasim and John and Matt and Al and Nathan are here. Is it Al or is it Lewis? Dang it. I'm sorry. There's a dude named Al that sits in that seat.
You have to restart the whole video now.
No, I'm going to let it go. Non-rehearsed. We're doing it live. Anyway, so on this PowerPoint, which I'm not going to go over, I'm just going to remind you to look at the PowerPoint and take notes on all, vectors, vector notation, direction and sense, and all those kinds of things. Oh, right triangle business, the trigonometry stuff. We're going to need Pythagorean theorem. We're going to need, if you have no idea what I'm talking about, then I'll try to teach it to you. We're going to need sine, cosine, tangent. If you have no idea what that is, we're going to teach it to you. And then eventually you get to, I think, what appears to be an example. Look at the example. You don't need to take notes on it. That's pretty much true for every PowerPoint. If it's examples, then you don't need to take notes on it. But if it's notes and concepts and things, then you do. So anyway, there's the PowerPoint. Let me minimize that. Come back to this maybe. And so notes on the introduction, notes on the resource, and then when it comes to the procedure itself, I'm mostly throwing out the instructions. Nathan and I were talking about this just a moment ago. When it comes to vector problems, I want you to solve, I'm doing air quotes, solve the entire vector situation. Just like in circuits when I told you to solve the entire circuit. I want you to solve the entire vector. Actually, I think these are called free body diagrams. Actually, they're not. We'll get to free body diagrams a little bit later, but these are just pure vector problems. And vector problems are about direction mostly. Actually, that's completely what they're about, because a vector is a quantity with direction. And so in this particular problem, we sort of base it on the XY axis. I don't know if that's visible on the screen, XY axis. That kind of looks a little fadey. And then there's a vector here at the origin that goes like that. And I think it's a 30 degree angle. And the vector is called A. It could be called F for force. Actually, I would call it F for force, but they're using A. 5.0 newtons. N is a newton, the unit of force. And I think that's it, right? And that's it. So I'm not even going to look at the instructions. Nathan, Nasim, Lewis, his name is Lewis. I'm not even going to look at the instructions, because they ask about what direction is it, what's the magnitude, what's the vector, all this kind of stuff. So I don't even care. I'm just going to solve it. How do I make this go full size? Nothing's happening. What do I do? Stop share? But I hope it's still recording though. In this problem, what this is really about is if you have a force vector, in other words, this is a force of 5 newtons that's being applied in this direction, which is 30 degrees from the negative y-axis. So when it comes to direction, you can describe it a lot of ways. I call it 30 degrees counterclockwise from the negative y-axis. And if you remember trigonometry, you could even call the positive x-axis, you could call that 0 degrees. And if you called that 0 degrees, then you could say that this particular vector is 60 degrees below the horizontal x-axis, and the positive horizontal x-axis. And this reminds me, Nathan and Lewis, his name is Lewis. This reminds me of the Autodesk Fusion 360 design we were just doing, when I was confused about whether it was a 30 or a 60. This is purely a coincidence that we're also dealing with a 30. But just so you know, this unlabeled angle is also 60 degrees. That unnamed, unlabeled, oh my goodness, that angle that you don't see is 60 degrees. We're going to deal with the one that's 30 because that's the one that they gave us. And so in this kind of situation, the force and the direction give us what we call components. These are components. It's actually right on top of the y-axis, so you kind of have to imagine that. These are components of the resultant vector. Now that's kind of backwards because result means what you get, but it's backwards because this is what we are starting with and it's the components that we get. So this just coincidentally sort of backwards, but this is called a resultant vector. And then this is called a component, an x component, and then this is called a y component. And already I can tell you, and you probably would agree from your math or trig or whatever math lessons or concepts you have learned and that you still remember, is that I can already tell that this a component in the x direction is going to be positive. Does that make sense? That this is going to be a positive value because we're moving to the right and on an xy coordinate plane to the right is positive. And then I already know that this a sub y, this one's going to be negative in the y direction. So at this point, I need to know, or we need to know, what is that a sub x value? And what is this a sub y value? And some of you might already know. Some of you might already know the answer. And if you do, don't tell us yet, because this is one of those special right triangles. It is a 30, 60, 90, it turns out. And when you have a 30, 60, 90 with a hypotenuse of 5, it turns out that the other two are something really simple. And you might remember this, you might not. I actually hope you don't. So this A is the resultant vector, and this A and this X, well, these are sides of a triangle. And if you remember the sine, cosine, tangent business, and even if you don't, I'm just going to tell you, this 30-degree angle, the relationship between this 30-degree angle and this side, this is called the opposite side because it's the one that's furthest away from the angle. If you were measuring this angle instead, well, then the opposite would be a different one. We always are referencing it from the angle that we're sort of analyzing. And then this a sub y component vector, this one we call adjacent. Is this good so far? Is this what you remember from your prior knowledge? So this a sub y is the adjacent, this a sub x is the opposite, and then the a itself is the hypotenuse. Now, the reason that we need to know which one's which is because of this. Remember this?
Yes.
I'm glad you do, because sometimes if you've never seen this before, I mean, it looks like a foreign language. The sine of theta, theta is a capital theta from the Greek alphabet. That's the traditional variable we use for angles. And the cosine of theta, that's the angle. The tangent of theta, that's the angle. And sine is equal to, let me see, so, ka, to. Remember that? So,
yeah.
So, S-O,
yeah.
H,
yeah.
S-O-H, so, ka, A, H,
yeah.
And then to, It really is like I'm speaking like Aztec right now. So katoa. And so the O, of course, is the opposite side. Remember, that's the opposite side in this one. And then the hypotenuse side, there's the hypotenuse side in this one. And then the adjacent, ADJ for adjacent side, here it is there. And the hypotenuse. By the way, if I get one of these mixed up, then everything's going to be wrong. And then the opposite, OPP, ADJ. So is that what you remember from whenever you were taught this? And then there's also, which is sometimes useful, there's also a squared plus b squared equals c squared, which you could also say x squared plus y squared equals r squared, if you want to think of it that way. It's the same Pythagorean theorem, but in this case, x, it's the x component, and y, it's the y component, and then r is the resultant. So far, so good. We haven't done anything. We've just set this kind of up.
You could add like sine to negative, the power of -1.
You're right. In order to solve for theta, he's right. Whenever you're trying to solve for theta, you would take the inverse of sine, and that's what Nassim was talking about just now. Well, we have the theta, and we have the hypotenuse. So if we have the theta, have, and if we have the hypotenuse, have, and we're looking for the opposite and the adjacent, we're looking for the opposite and the adjacent, you probably would agree that we know which of those three trig functions to use. I hope you agree that it's sine and cosine. So since we don't know the opposite and adjacent tangent is going to be really impractical to use. And since we don't know X and Y here, Pythagorean theorem is going to be impractical to use, but you could actually still use them in a later step. You could use them in a later step, but it doesn't make sense to use them at the beginning. What does make sense, and what's always the most comfortable for me, is sine. Seems like sine is just the alpha dog of trig functions. And so I'm gonna use the sine. Make sure that I stay on the screen, because I'm gonna do some sliding probably. The sine of theta is equal to, what do we say? Opposite over hypotenuse. Please make sure I don't make a mistake. And then the theta itself is 30 degrees. We say that's the sine of 30, and we'll calculate that in just a moment. And then the opposite, which one is the opposite here? The a sub x. And then which one is a hypotenuse? It's that a, which is a 5. So now we have an equation with one unknown. And what I would like to suggest, even though you don't have to do this, I would like to suggest to go ahead and multiply that 5. I am recording, Ms. Hoffman, but please come in. You are welcome. Ms. Hoffman has just arrived. Ms. Hoffman is both my best friend and a chemistry teacher at Liberty High School. We're doing vectors. It's so thrilling. Look at Lewis. His name is Lewis. He's losing his mind with delight. So the sine of 30 degrees, before I calculate that, and Nassim, it looks like you're ready with that scientific calculator. The sine of 30 degrees will be multiplied by 5. So I'm just going to go ahead and write a sub x equals 5 sine of 30. And so scientific calculator time. And when you whip out your scientific calculator, for me, I'm using an iPhone, so you got to turn it sideways to get the trig functions. And Nassim, tell me if you agree that the sine of 30 is 0.5. Do you agree with that? He's thinking.
Sine of 30.
The sine of 30 degrees is 0.5. Can anyone check that on their scientific calculator? This is where they have to engage. Excite, empower,
Right?
and engage. It is 0.5. Thank you. Even Ms. Hoffman, with her limited math skills, was able to give us
Wow,
that.
really, man?
Yeah, I'm sorry.
Whoa.
I'm sorry. I will be punished later. So 0.5 is the sine of 30. And then 5, I hope you agree that 5 times 0.5 is a sub x equals 2.5. And it is newtons, just like its parent, that resultant. Does this make any sense so far? And by any sense, I mean, it doesn't have to make perfect sense. Just if something up there is like, okay, I understand what he did. I don't understand everything, but I understand that one thing. So now that we have a sub x, and remember, Nathan, we're trying to solve for everything. They gave us 30, we got it. They gave us the a value of 5, we got it. We just calculated a sub x. And so now it is time to calculate a sub y. Well, let me think about this. A sub x, we use the sine of 30. A sub x was the opposite. And so we use the opposite over hypotenuse, we use sine. Well, now for the adjacent one, if you believe me that a sub y is adjacent, meaning next to, if you agree that we're going to use this now, it's a cosine. It's the same process. The cosine, is that on the screen? The cosine of theta is the adjacent over the hypotenuse, right?
Mm-hmm.
And then this is going to be the cosine of 30 equals the adjacent, which we don't know, is a sub y. And then the hypotenuse, which we do know, is still 5 for that resultant. And I'm going to multiply the 5 times the cosine of theta. And I'm going to, what's going to happen? I'm going to get a sub y is equal to 5 cosine theta. And then the cosine of theta, Nassim, tell me if you agree with this. Theta, what's the value of theta? Theta is 30? Sorry about that. I was doing such a good job. The cosine of 30, do you agree that it is 0.866025403784439?
Yeah.
Okay, and too many digits, clearly. We don't want to deal with that. So I'm just going to think 0.866 and then multiply that by 5. And I get 2.165 up down the line. And so a sub y is equal to what I'm going to write down as 2.17, just because 3 digits is enough. I would get tired if I had to keep writing numbers after 3 digits. And then, let me zoom out a little bit. Then a sub y is solved.
I got 4.3.
Oh no, did I mess up? I did mess up. Oh my gosh. Thank you, Naseem. I did not intentionally mess up, but it is nice to mess up and then have it checked. Times 5. Yeah, I don't know what happened. I don't know what happened. It's okay, another error. And this is exactly how you handle errors in your notebook. Make sure you cross them out with one line. 4.33 newtons. That is the answer. Okay, please forgive me for having that incorrect. I don't know if the light is better or not better. So that's it for now. That's the easy one, by the way. That's the easy one. And so that's it for now. I'm going to stop the recording and we will do some of these in class. Say bye-bye, John Pham. He said bye. Okay, oh, wait, he said bye. Bye.